So today I'm going to be talking about an initiative that we have called Spirit Cognitive Robotics. First, an overview of what Spirit is. Spirit, we are one of the leading global aerostructure suppliers. We design, build, and sustain large aerostructures like fuselages, propulsion systems, wing. We used to be Boeing until 2005. And we became an independent entity in 2005. And since then, we've been diversifying our portfolio, our customer base, and our capabilities. The picture that you see on the right, all the blue parts are the ones we produce at Spirit. Of particular note is the 737. The complete fuselage the fuselage structure is built in Wichita, where I'm from. That's where our headquarters is. Another important point here is that we have about 20 million square feet spread across 12 locations across the globe. Most of this 20 million square feet is shop floor. So in terms of the state of automation, this is not Spirit. This is, I believe, Tesla. We'd be very happy and content to have our factory floors look like this, but we are not there. If you look at the data in the last 10 years, apparently the robot sales have tripled, and most of the growth has gone into automotive. And in aerospace, we are under the others. And in fact, there's been a negative growth in 2019 and 2020. So that kind of paints a realistic picture of where we are in terms of automation. And robotics, I think, is kind of a proxy for generally all kinds of automation that we do. If you see these kind of images, you can see that mostly it's all manual operations, and that's what dominates our shop floor. We have strong motivation to move and have more automation in our factory floor. For one, we need to, we have some unique manufacturing technology and processes, which our competitors cannot replicate. Even sometimes our customers cannot replicate these technologies. We need to be able to continue to retain that leadership. And secondly, I think coming out of the pandemic and then the last 3 years have been really hard on our industry and particularly for our company. So we have very strong motivation to enhance productivity and quality, efficiency all through our factory floor. And on the other side of things, we are recovering from the challenges of the last 3 years. And then now we are looking at growing back to the previous volumes in our production. But not just that, I think we have to exceed that. And pretty soon, I think in 2 to 3 years, we should be producing more airplanes than we were prior to the pandemic. So, and I think this time we have to do it differently because we lost some of the capacity that we had during the last 3 years. So automation is really key for us. And I think you heard some of the challenges with Lockheed earlier, similar industry. So high mix, low volume, it's a big challenge. That's one of the reasons why we cannot justify more automation in our factory floors, because usually we don't have the business case to do that. And then the fragmented ecosystems, I'm sure all of you here are familiar with all the challenges of integrating all these different sensors and robots and working with them. I think we talked some of it in the workshop today. So those are big challenges, but I think we can work through them. So we can't solve the fragmentation problem, but we can design our solutions around it. And then the third big problem is if you end up designing a solution, we have done that. You have the challenge of you end up with a complex system, and you have the challenge of training your workforce to manage that big complex cell. You need to train your maintenance folks. You need to train the operators to use that. So this becomes a challenge. I think these are big challenges that we see, which is kind of preventing us from going all in on automation. And I think one of the important things, we talked about 20 million square feet of space. The scale is of importance. We cannot design point solutions, and we won't ever be able to automate our factory floors like what you saw in the picture, in the Tesla picture. So in order to get there, whatever we do, we have to do it at scale. And that's what we are attempting to do. So some deep dive into some of these challenges. I took example of one of our first cells that we did. This was an inspection cell. It was in one building, two aircrafts, 737 and 767, both are fuselages. And we wanted to develop an inspection cell for fastener head heights. So we have two fuselages, but each fuselage has a variant. So the CAD is different, the geometry is slightly different, the fastener types are different. So you have all these variations that we have to deal with. And then we started with fasteners, but then quickly we started looking into scratches and dents on the skin, aircraft skin. And that requires different sensors. Some sensors can do multiple jobs. And so we have all this in the mix. And then the challenge is that for 737, we have 14 stations where you need to have the inspection done. On 767, we have 4 stations. So with all this mixed up, I think whatever application we develop has to satisfy all the conditions. So we have to have one solution, and then which can address all of this, because we don't have a chance to do multiple solutions because again, because of the cost. In terms of fragmentation, by the end of developing the solution, we ended up with 4 different kinds of sensors. We have motion capture, we have cameras, 3D cameras. We have 3 sensors, one for dents, one for fasteners, one for scratches. And we had to integrate all of this. And then when we deployed it, based on the feedback from the inspectors, mechanics, so the way the application had to be deployed was that the inspectors preferred smart glasses, the heads-up display, because they wanted their hands to be free when they're scanning. And then the mechanics who went in and to fix the fasteners, they wanted cell phones. They just went around the airplane looking at cell phones. You'll see some of these videos a little later. So we ended up having multiple ways to deploy these applications. So we had cell phones, smart glasses, tablets, and a large touch screen. So we had to deal with all of this. The challenge here is that we can do this one time, but we need to be able to scale this, not just in one building, but inspection. We do this kind of inspection across multiple aircraft programs. So we need to be able to replicate this. And once we get past this, one of the challenges is today, these inspections are done by mechanics or not engineers. So this is a node graph from the same application. It's a small slice of the node graph. Imagine trying to train our people to understand this and debug and fix issues during operations. So we have to abstract all this complexity away and make it easier for them to consume this and use this technology. So this is a big challenge. If you can't get this right, there is no production deployment. It'll never see the light of the day. So given all that, so we came up with this framework called cognitive robotics. At bottom, it's nothing but a set of ROS libraries that we use. And at this point, I think we have to thank Spuri, ROS Industrial, for us to get Spirit started on this journey. I think they deployed one of the first ROS-based cell way back in 2015, 16, when that was before my time at Spirit. And Spirit was really ahead of its time in terms of deploying this kind of an advanced perception-based, ROS-based production cell, so for painting. So we continued that journey, and then we wanted to kind of look at how do we scale that, because that was one cell, but we wanted to do multiple cells. So what we are trying to do here is put a strategy around how do we develop these modules that we can scale to multiple cells, multiple solutions. Even if it's an inspection application, how do we change parts, change from Boeing programs to Airbus programs, and so on. So this is just the way we think in terms of how we structured our framework. Communication, it's all ROS. I mean, that's, we've settled on it. I think any sensor that we have to integrate, we have, I mean, if you're lucky, we have drivers. If not, I think we build our own drivers. Like some of the sensors that I was talking about, they are highly specialized inspection equipment. So they don't even know what ROS is. So we need to build those bridges and then get them onto our platform. So that's one. And then, as I said, sensors, I think we have all kinds of different sensors we've been using. I think today, we have a library. So we made it so simple to integrate new devices into our library that we have a template. So you have a new device. I mean, it requires a bit of work to kind of develop the drivers, but there is a common framework, common message structures that we can use. So that makes it easy to swap things out. If you don't like a certain 3D camera, we can swap it out with other OEMs. So again, that's something that we have built those templates. And most often we use perception to translate it to some kind of a useful task for the robot. So we have different kinds of applications. Again, within a very narrow aerospace manufacturing domain, we have drilling, sealing, scanning, sanding, imaging kind of applications. So we needed a common messaging format, common data structures to work across these different applications. So we developed these tools. This is the common data structure across all these applications. We have tested it, and we've been successful in using this. We translate the information that we get from these sensors to these tasks, which we can feed to the robot. And I'll show you different examples of different kinds of robotic applications which use all the same framework, same modules, same data structures to do that. And one of the key parts of developing an autonomous system is ability to make decisions for the robot to make its decisions on make it autonomous. We heard a few important information about behavior trees. Looks like that's really popular. I mean, of course, we use control logic, state machines, but they don't really scale well. Behavior trees seem to be really popular. I did try looking into behavior trees, but I found the symbolic AI tools, like there is a tool, there is a paper called Strips back in 1970s from Stanford. Not sure why that is not more popular than behavior trees, but it's really simple architecture. So what we use is, it's based on actions. So if you have an action, action has a certain prerequisites and it has a certain effect. And that's all you need to know. There is a planner behind it, which is, we don't have to worry about it. I think the planner, what it does an A-star search through the graph, and it, based on the preconditions and the actions, it searches through that and then comes up with a sequence of actions that we perform. So the burden of sequencing these actions is with the AI and not with us. For the roboticists, it's all about just, you can develop these actions in isolation. We just have to worry about what do I need to be, what is the system state I need, and then what is the action that needs to be performed, and then what's the effect that's going to result in. So you need to just concern yourself with that and let the AI do the sequencing for you. So I found this to be really simple. I could not find any open source libraries which implemented this. There are gaming engines which do this. In the gaming world, they call it goal-oriented action programming, GOAP. But I couldn't use it. So I ended up building our own. It's open source on GitHub. If you look at action graph, you could probably find it. So it was really simple to implement. It works. We worked across different robotic applications. But I think probably it's all moot now. I think in 2 years, probably we'll be looking at large language models trying to do this for us. So we already heard that Movit is trying to do this. So in terms of interaction, so this is really critical for us. One of the challenges of this complex robotics applications is the endpoint. The mechanics, I mean, we can't expect to have engineers operate these cells. I mean, we don't have a business case to justify that. And we need to have mechanics, the same mechanic who's using his manual inspection processes to use this instead. Yeah. So when we deploy this, we can't have a lot of training and education to those operators. So it has to be really simple for them to use. One of the ways we measure success is by the amount of time the operator spends in front of the computer. So we need to minimize that as much as possible. And the way we try to do that is give them very user-friendly, something that they like to use, the interface, that's something that they like to use, and they don't complain a lot about. And they even wanted light theme, dark theme, so we gave them that. So, so I think it's really critical for them to like this, for them to use it and give good feedback to their managers so that this will see a long life in the shop floor. So, and the next level of challenge is once we convince the mechanics, we need to convince their bosses that there is value in deploying these. And that's why we have all this charting abilities so that the managers get some value out of these tools. So these charting libraries are common across all our applications. And the whole HMI that you see here, we have multiple applications. They use the same HMI. I mean, it was really challenging to achieve that, but we've been able to kind of modularize our applications, whether it has a robot or it was without a robot. We have the same HMI working across different applications. So we have all the sharding abilities which can work across various applications. The data structures are kind of common. You can configure these charts in a config file, and then you'll be good to go on a new application. And the last set of people we have to convince that these solutions are useful. I mean, kind of easy in a way because we can just show by numbers, is our finance teams. What we have done is we have developed Excel templates for each cell that we develop. We have an Excel template for calculating ROI and payback periods. So what we do is even before we start proposing or designing a new cell, we start collecting some information about the CAD, the kind of part that we work with, and then we use that to build this information, looking at what is the current effort being spent, what is the labor effort, what is the current state, and then what is the new investment that we do in terms of capital, in terms of recurring investments. So we build this, and then this Excel template throws up all the numbers that the finance team is interested in. I mean, we know what they're looking for, what kind of payback periods and what kind of return on investment. So we ourselves can calculate that, and we can see if our solution really will make the cut in future. So we don't end up spending a lot of time later justifying why things are so expensive. So we can, if things don't work, we have the option to go and redesign our solution. Maybe don't use two robots, use one robot, and then you can still do it. So that this has been really critical to sell our solutions. So with all of this, what do we get? We start with certain packages, either maybe ROS native packages or our own the package that we have built. We build an application layer where we combine all these packages, create a new application. So this one here is called a Spiffy. So what we do is, the Spiffy is an inspection application. It's a platform for digital inspection. We can inspect fasteners, dents, scratches. We have about 7 or 8 different devices that we use, and we combine all this data that we can consume. So, but this is an application by itself. So when we decide to deploy this, for example, in this case, the 767 airplane, so we need to configure this to work with a particular product, particular airplane, particular standards. So we combine those. Most of this work at this level is mostly config files. We don't do any more coding at this level. So we deploy this application. So we had a situation where we need to morph this manual inspection cell, which was ROS-based, to a robotic cell. So then we go and add those packages. We use 100% of what we develop for Spiffy, and then we develop this new app with the robot. Again, we configure that to work in a particular cell. FLE is fixed leading edge. So that's how we do it. So at least on inspection cells, we have gotten up to a point where we have promised our end customers, the operations folks, that you give us the requirement in some terms of the CAD files, any engineering drawings, and we'll get back to you with the solution with the software completely configured in 3 weeks. I mean, the hardware is the long lead time items. Outside of that, we can deploy a new cell in terms of software and all the configuration in 3 weeks. And we have shown that. Actually, it takes 2 days to get all the configurations done. Most of those 3 weeks will be chasing all these files and what's the latest. And so that's where most of the time we spend. So it is possible to get there. So just not all talks. I think we have the 737, 767 application that we talked about. It's live. On the 737 cell, we have one of the world's largest motion capture setup with 260 cameras looking at 14 different stations. And we have this inspection cell. I think you'll see the video and probably get an idea of what we do. So it's called Spiffy, stands for Spirit Feature Inspection. So that's one of the devices. And there's a heads-up display. The operator looks at it. So it's being tracked by the motion capture cameras. And then this is the software interface, the end user sees. Actually, there are only 3 button taps to load a new line unit. Everything else is optional. The mechanic just has to spend 10 seconds in front of the screen and then take the scanner and go. And this is what I was talking about. This is a mobile phone interface. The same thing here, working on mobile phone. The window that you see is RWiz. So this one here is an example of using the same platform. So one of our leaders wanted us to do images instead of doing fastener head heights, they wanted to capture images and stick it on the fuselage. So we got this done in 2 weeks. So in 2 weeks, we were able to use all this modular libraries, just that part where we replace fasteners with images. We were able to kind of do that because of this framework that we have. And here we have multiple devices, actually 4 devices in the scene. Actually, there are 2 more that we can use on the cell, where we can use these devices simultaneously and then collect all this information, and it gets aggregated in our reporting tool. So Robin stands for robotic inspection. So this is SPIFFY, but with the robot. This is under development. We have done some testing. Next year, it's going to be deployed in production. There are a couple of applications that we're looking at. This is a large fixed leading edge on one of our commercial aircrafts. So this is going to be one robot servicing 8 stations. You see 4 here. And it's a KUKA robot. So with this special scanner, it can go around the cell, and it is completely autonomous. At least that's what we're targeting. We probably would have 2 robots, one doing fasteners and dents, the other one doing scratches. So it can go around, plan, and then go on the cell, do it in night shift, lights out, automation, and then get the results. So the other one, again, if you've seen this, the theme, you see the HMI is same, not just the HMI, a lot of the code behind is also same. They're all based on the same cognitive robotics platform that we've been using. And large thanks to SWRI, because some of the robot drivers, I think we're using from the ROS Industrial Library. So we're using those. This is for Navy robot. This is a sealant application. This is from last year. We were testing our technology in a coupon. This year, we're going to be doing this on a large wingback, which can probably as big as this room. So it's a really big panel. And again, we are moving away from offline programming. So we program the robot by teaching it. We use motion capture to teach the robot where to seal. And you see this is being, the seams are being captured from the motion capture. And the robot plans itself and then goes and seals. So there are 2 layers of control. So there are 2 lasers. The seam tracking is being done using the lasers. And all the other part, which you saw, is being outside of that. And what you see in the scrolling text is the action graph that we talked about earlier. It's being planning in real time, and then executing all these actions. So we have gotten up to a point where we are making use of these technologies in production. We are finding some real useful, actionable insights. Just one example from the SPIFFY application, there were some pattern of defects, non-conformances in the airplane, which we saw for 2 or 3 airplanes. And this was able to kind of point down where things started going wrong on what line unit, and then what was the issue, which zone had the issue. And then we were able to track it down, do the root cause analysis, and then fix those issues. And that's how we are using it. And we have a lot of such examples. And that's why I was talking about the analytics library. Across all the applications that you just saw, and then we have a few more, we collect all this information. It's available to the end user if they want to look at it. We have all this charting. And typically, it's not the mechanics or the inspectors who look at this. It's the managers who look at this, and they have to justify the root causes and then see how to address them. So all of this is available on all our applications. All we need to do is have the same database structure, configure that in our config files, and all these charts are ready to use from the get-go. And we can do all this correlation analysis. So all of this is part of our library. And we have spent time developing this one time. We don't spend any more time on this. We just do config files. So where we are today is you saw 4 applications. We have more, some of them in the pipeline. And more importantly, these applications, once they're mature, and we plan to deploy them in multiple locations. I think we started out with the challenges of scale. That's what we're trying to solve. I know a lot of people here they'll come up with solutions which are really wonderful, but how do we scale this across 20 million square feet of shop floor. So that's what we're hoping to achieve by this. And so far, it's looking good, especially on the inspection side. I think we are doing okay. We have lots of ideas and where we can use in logistics, asset tracking, different automations. So we have all these different themes going on. And the vision is to use these kind of technologies. There are lots of challenges, but this is where the vision is to do this at a part level, a system level, assembly level, integrate all of this information, get a bird's eye view of all of our processes, our quality metrics across the organization, at least for one product. I didn't talk about the cybersecurity challenges that we have. It's a big challenge. We haven't found a solution yet. We are an aerospace company. We have a defense portfolio. It's really challenging to deploy these applications in production. I mean, we have done this because of some special considerations on each of the cells, but I think that's something that we have not talked about. That is something that we are still working on. So that's where we are.
It's really great. Bharath Rao. Any questions for Bharath and the work that's going on in Spirit? Really impressive work. Yeah, gosh.
So you had a lot of different sensors there. So I don't know if you can tell us, how did you tackle the calibration problem?
Oh, yeah. Yeah, it's been a really challenging problem.
For a number of sensors.
Yeah. So of the critical one was each one comes with its own challenges. One of the biggest challenges was in the 767 fuselage is as big as this room. And we are tracking fasteners, which are not designed to any drawing or engine spec. I mean, the 767 was designed 40 years ago, and the drawings are still on Mylar papers. So you can expect things to be not as per the drawing. So the way we have tackled it is we are using motion capture. As we collect the data, we use the data of the fasteners to locate the fuselage, not the other way around. We do start with locating the fuselage. We have tooling holes where we put the trackers in, and we start there. And then the system itself, again, we don't want the burden of calibration for the operators. So we use the data coming from the fasteners, the inspection device. We use that. Luckily for us, the device can give us the locations of where it thinks the fasteners are. And we use that. In fact, with every scan, the fuselage is moving. I mean, the operator doesn't notice it, but it's moving, and it's moving quite a lot. But the end effect for the operator is that they don't feel it. They just keep going scanning. They can complete the whole scan of 8,000 fasteners in about 2 hours. So yeah, it's a challenge. I mean, if we're still dealing with those in the sealant applications, last week, that's what we were working on. So yeah, I don't have an easy answer for that.
We talked about calibration over here in the last side workshop, right? So definitely an area.
It's a different, yeah, with each sensor, with each application, it's a different problem, but yeah.
Excellent. Thank you, Bharath. Thank you for taking the time.